All right, hello everybody. Mr. Keller here, March 30th, 2020. Power polynomial rational functions. We're doing power functions lesson. Actually, I put lesson 3 because we're skipping over a cool thing I was going to have you guys do in class. But this is technically lesson 2, but it's going to be called lesson 3. Well. Here's the deal. Power functions, the chart that 7 out of 18 of you did. Let me say that again. 7 out of 18 of you did the chart on power functions. To those 7, this is for you. Thank you, muchas gracias. Thank you. Yes. To the rest of you, get them in. All right. So today we're going to learn how to graph these things. If we're not counting boxes, then I think we're doing way too much work. We're going to figure out what K and P do. Remember, the form that we're looking at for K and P, so you don't think I'm nuts, is the basic form of a power function, and that's where we're going to start here. A power function is a function that is raised to a power, because we're boring math people, and for God's sake, why not call it a power function when it is a function x raised to a power? So input, output, power. Power is a constant. All right, the x is going to change. The k is also a constant. So the k and the p represent numbers that will stay standard for each individual equation. X will vary as usual. F of x will therefore vary depending on what the power p is and what the constant k is. Alrighty, with that said, transformations, obviously we're going to do transformations and we have to go over negative exponents. So here's the deal, power functions of this form. All right, make a sketch of the following scenarios. P is even and positive. So here's scenario 1, P even and positive. K is positive as well. All right, how could that possibly look? Well, I'm hoping if you did your chart, this is going to be extremely easy. But if P is even and positive and K is greater than 0, we're going to have a parabola. All right, it doesn't have to be a parabola exactly, because if P was to the 4th power, then this thing would maybe look a little bit more flattened out. But basically, that's the overall shape. All right, touchdown, whatever you want to say. K is greater than 0 means that it's concave up. All right, concave up. All righty. All right, so even and positive means 2, 4, 6, 8, 10, 12, numbers like that. If I have to explain that, I probably shouldn't have to explain that. All right, P is even and negative. So P even but less than 0 this time. K is also greater than 0. So here's an easy, quick sketch on that one. Let's see. All graphs where P was even yet negative looked like what I like to call a volcano, or the Atari symbol if you're a gamer. With K being greater than 0, it means that we're talking about still concave up. All right. But we're talking about being above the x-axis, Why? Well, K right here we know is the vertical stretch factor. Woo! Okay. Number 3. Here we go. Let's see. Odd and positive. So I'm going to just get these down so I can go to the big screen. Big screen being a whiteboard. 8.5 by 11 whiteboard. Ay. Times have changed. All right, in number 4, we're going to have P odd and negative. We should have K less than 0. Oh, no, I guess we're all just doing K is greater than 0. That's weird. Not very thought-provoking on my end, but that's all right. Okay, here we go. Let's see. Push this up a little bit so you guys can see. There we go. And let's see what we got. Draw some axes in. Forgot my arrow right here. All right, so odd greater than 0 just looks like a cubic of some level. So like a graph that looks like that. Pre-calc class back in the day called it the snake graph. I don't quite get that, but whatever. Works for me. All right, now if we're odd and negative, we got the hyperbola, which is the best graph ever. If you don't understand that, that was hyperbole with hyperbola. Hyperbole with hyperbola. Yeah. So anyway, that was a fun little thing. So those are our basic shapes that we're going to play with. On your chart, you had a couple extra ones. that involve that. So, or that involve some different graphs. But these are the main four that we're going to do. All right. So this is to the third, to the fifth, to the seventh, to the ninth. This is, we're talking negative first, negative third, negative fifth, negative seventh, negative ninth. They all resemble some shape like this. Now, when I say resemble a shape, I don't mean they're exactly these shapes. They resemble the appearance of these things long term. They will change drastically short term. By long term, I mean go out to infinity. Short term, I mean, where the roots are and the y-intercepts are. Alrighty? So pretty straightforward. All right, let's graph one of these pups. But before, what am I torturing you with now? Oh, what will K have the effect of changing K, making K negative? Well, if we go back here, if K is negative, then we know from previous lessons that we basically get a reflection over the x-axis. Okay? So that's what these are going to look. I'll do them dotted. And then let's see, that's going to look like this. And then this guy's going to look like that. So the basic transformations counting boxes thing that we've been working on all year long. So, things to still think about. All right, negative exponents. Do you remember what they do? Dear God, I hope so. If we're going negative exponents, x to the negative first, we know is the same as 1 over x. Okay. And then what else am I working with here? Rewrite kx to the negative first. Okie dokie. So kx to the negative first is going to look like this. All right. X to the negative second is the same as 1 over x squared. That's what you should have found in your charts. I think everybody should be able to do that. And we're supposed to rewrite kx to the negative second, which is not a challenge in the slightest. So here we go. Kx to the negative second is the same as k over x squared. All right. Graphs that'll look like that, assuming k is positive, it'll be some version of this. If k is negative, it'll be some version of that. Okay, this guy right here, if k is positive, we get the best graph ever. K is negative, we get second best graph ever. Okay, that's that whole section of notes. Easy peasy, we're flying. Keep this a short YouTube video. All right, now we got to graph this guy. Oh my God, I can just hear you now in class. Wait, what? It doesn't look the same as kx to the p. Correct. It does not. So I'm going to erase this stuff here. And we'll flip-flop back and forth. I feel like this is going to get a lot of views for satisfying if you watch somebody erase a board. All right. And don't leave any spaces. So I can probably put the hashtag pleasing or satisfying or whatever that weird niche YouTube stuff is. Yeah. I'm also thinking about getting a nice microphone, like a giant microphone, super powerful, that I can place really close to my mouth, turned up full volume so that you can hear every nuance of my words. Maybe I'll eat something too, so that could be the ARSM or ASRM or ASMR or I don't know, whatever. Abdul knows. He's the one who told me. All right, so here we go. Page 402, number 13. We're going to try to graph this bad boy, but first we got to come to grips with the fact that this is a power function. All right, so I just got done telling you a power function looks like kx to the p. And that right there does not look like this. So what do we do? Well, what we're going to look at is we're going to think transformationally speaking. What does this minus 3 do? Well, it takes the graph. What graph, you might ask? I don't know. We're going to come back to that question in a second. But it takes whatever graph we're starting with and shifts it right 3 units. Okay, what does this plus 4 do? Shifts whatever graph we're starting with up 4 units. Well, gee, if I took, so I'm going to circle those so they don't think they're part of the problem. But if I started with this graph, the standard form of a power function, I wonder what would happen. What would it look like if I shifted it right 3 units? Oh, I think it would look like that. If I shifted it up 4 units, I think it would look like that. Hey, that's the fixins of this graph, f of x. So what is this shifted right 3? It's the y that we started with. All right, right 3 up 4. All right, so now if I want to graph this thing, okay, all I need to do is think about transformations. What is this the graph of? Well, to me, the exponent power stands out like a sore thumb of being a 1. So this graph is, more specific, 1 over x shifted right 3 up 4. So I'm going to draw y equals 1 over x from our charts. It's going to be the land of Gretsch. All right? Not quite a full-on graph where we're plotting every single order pair, but better than a sketch where we're just winging it. Alrighty? So this is y equals 1 over x. I'm going to leave that there as my transformation. And then now we know things about y equals 1 over x. We know that it has horizontal asymptote y equals 0. We know that it has a vertical asymptote x equals 0. We know that there are no x-intercepts or y-intercepts. Okay, so it looks like that. So what happens if I take this graph, this entire thing in blue here, and I kick it over right 3 units and up 4? Well, every single one of these points is going to move the exact same right 3 up 4, right 3 up 4. So that's going to give us a whole lot of roots and y-intercepts. But we got to think, if I shift the graph over 3 units to the right, what will happen with the vertical asymptote? It will have to move 3 units to the right. 1, 2, 3. So I'm going to use a different color. I'll do all my graphs. Actually, no. I'm going to do that in blue. So 1, 2, 3. X equals 0 now becomes x equals 3. So this graph, this f of x graph, has a vertical asymptote of x equals 3. This should make sense. You were taught this in previous courses. Okay? I'm going to close this out now so it's not sitting there. But you were taught this in previous courses. What is the only value of x that will make this denominator equal to 0? 3. What happens when you divide by 0? Uh-oh. It is undefined. What happens when you take undefined and add 4? Still undefined. What visually did we use to represent undefinedness? Vertical asymptote. Okie dokie. The horizontal asymptote is usually y equals 0. What happens if I take the entire graph and I kick it up 4 units? That means the horizontal asymptote will follow suit and it will go up 4 units. So it will be way up here. I'm already annoyed at myself for not giving myself enough graph, but that's okay. That's why we erased. Mother Queen and Daughter Princess, are you making fun of me in there?
Yes.
Excellent.
Nope.
Very good, Soph. All right, so I'm going to adjust so we get a little bit more room. And then let's see what happens. I'll go for black on this guy. All right, so vertical asymptote x equals 3, horizontal asymptote is going to be y equals 4 now. Okay, so how are we going to graph this thing? Well, this first section is pretty easy. This whole graph's got to go right 3 up 4. So we get in pretty good shape here. There is my new piece of graph. This guy over here, however, is going to go right 3 and up 4, which means it's now going to hit the y-axis somewhere, and it's going to hit the x-axis somewhere. Okay, so when I draw this through, watch this. Oh, you can't really see. If I draw this through, watch the pen. It's going to come down, hit the y-axis somewhere, hit the x-axis somewhere. All right, so it's basically going to be this shape right here in blue, right 3 up 4. Okie doke, so we got some work to do. That means we're going to have a y-intercept and an x-intercept. To figure out a y-intercept, it's still the exact same thing it's been since, 8th grade, 7th grade. All right. Jess, when did they learn how to find y-intercepts?
7th grade.
7th grade. So still, same old thing. A y-intercept is when your x value is equal to 0. So when my x value is equal to 0, I get 1 over 0 minus 3. So that's negative 1/3 plus 4. So that's what our y value is when x is 0. X is 0 implies y is equal to 4 minus 1/3. Well, 4 minus 1/3, I'm hoping That's not too hard for you. That's 12 thirds minus 1/3. That's 11 thirds. If you don't like 11 thirds, think about that. That's 3 2/3. We're going to wing it here. Here's 1, here's 2, here's 3, here's roughly 2/3. Okay? To figure out an x-intercept, it's still the exact same thing from, I don't know, probably 7th grade as well. To figure out an x-intercept, we're going to set the y equal to 0. So how does that look in our equation? Well, it's going to be f of x replaced with 0, and we got a little algebra to do. Okay, so to solve this, I'm going to clear the denominator by multiplying everything by x minus 3. So 0 times x minus 3 is 0. X minus 3 divided by x minus 3 is 1. Times 1 is 1. Plus 4 times x minus 3. So clearing the denominator. If that's too fast for you, this is pre-calculus. You've cleared the denominator since 7th grade. So try your best. Or rewind the video. That's fine too. So let's see. I'm going to get 1 minus 12. Which is negative 11. I'm going to add that over to the other side. So I'm going to get x is equal to 11 fourths. All right. 11 fourths. Well, that's almost 3. So 1, 2, 3. Back a little bit more. All right. So we've got pretty accurate points now to graph this thing. And I'm just going to sketch this bad boy out. We got to hug the asymptote, hit the y-intercept, hit the x-intercept, and hug the vertical asymptote as well. So our new graph is in black, which is pretty cool. Does it look like the blue graph shifted right 3, up 4? I think it does. All right, now here's the work you're going to balk on because it's actual work. That stuff right there, not difficult. It's in your wheelhouse by far. But the idea is you guys categorize things, thinks it's new stuff. All right, I'm going to speak a little German to you. Ha, va, jint, yint. That is horizontal asymptote, ha, vertical asymptote, va. Jint is x-intercept, x-int. If I said that phonetically, it would be jint. And then y-intercept would be yint. So if you remember your asymptotes and intercepts, all of this work goes exactly the same. It's a one-trick pony. Alrighty? Let's see. Make this video super long. It's the whole lesson, so you can watch it in stages. All right, let's see. We did that? No, we didn't do that one. We got to do this one. We should do one more, I think. All right, so now 402 number 13, graphing power functions. We've got a negative sign here. We've got an even exponent. Oh my God. We've got the minus 3. We got the minus 2. Holy moly. Let's see if we can figure this out. Now I'm going to go back to see if anybody follows a YouTube account for soothingness. Also, by the way, I have some beef. I created a YouTube account, put myself way out there. Nobody is following me from this class. It makes me sad. Very sad. My wife is following me. She doesn't even like math.
Nope.
My daughter Sophie is not following me either. Also sad, but she's 7. All right, new function. Let's see what we got. G of x equals negative 1 over x minus 2, the quantity squared minus 3. All right, this is where the chart comes into place. We're going to need to figure out what graph does this resemble. Well, it resembles this guy. 1 over x squared. 1 over x squared, in case you forgot the shape of that, it is the volcano, as I like to call it. It's this guy. Okay, so as you move x to right, off to infinity. As you move left to right, there's a vertical asymptote here, and then down from infinity and levels out at 0. So what do we know about the original graph? Horizontal asymptote, x-axis. Vertical asymptote, y-axis. Intercepts, nada. That's the OG original. Okie doke. I learned from my mistake last time. I'm going to leave that in the corner so then we can just refer back to it. And now I need some room. All right, so transformationally speaking, all right, we're talking about f of x equals kx to the p as our base graph. That p we know is equal to 2, so that's kind of cool. And in this form, it would be actually kx to the negative second. So that's why we took that little bit of time to talk about writing that in 2 different ways. K over x squared. All right, so now if we're living there, what does this negative sign do? Well, that's going to reflect this graph way over here over the x-axis, all right? What does that do? It shifts it right 2, down 3. So here's what I'm going to do. We're going to go into this, and we're going to have our power functions chart out. Some of you did this, some of you did not. 7 out of 18 kids did the actual assignment. Couldn't tell you how much that chart meant. All right, well, anyway, I'm shifting this right 2, so that means the vertical asymptote gets shifted right 2. Vertical asymptote's always drawn with dotted lines. And let's see, horizontal asymptote down 3, home skillets. We go down 3. I'm going to label my asymptotes so that they stand out like a sore thumb. There's my x-axis. There's my y-axis. We got ourselves a great graph. Now, some of you are going to be tempted to just do this. And just wing it. I ain't going to give you full credit. I'm going to tell you that much. And I would also like you to know stuff, especially if you're juniors. So that you can go and take calculus with me and actually know stuff. If you go on and you're a senior right now, I still want you to know stuff because that's the kind of guy I am. Alrighty? Now, how do we do it? Well, I got the asymptotes and intercepts done. So this guy right here, we got our horizontal and vertical asymptotes taken care of. Vertical asymptote, x equals 2. Horizontal asymptote, y equals -3. Those are graphed. Those are labeled. Ha, va, jint, yint. All right, we got the hard stuff now. I got to do the x and y intercepts. All right, well, let's see. Was I being a little playful there? Is it really difficult? No, it's not. Y-intercept. Still 0, comma, whatever we get. Well, let's take the equation and plug in 0. If I plug a 0 in right here, 0 minus 2 is -2. -2 squared is 4. So I am going to be left with -1/4. Okay, so the negative sign, 1/4, then -3. If I think about that, that is -12/4. Yes. Yeah, -12/4. Yep. -12 minus 1 is -13. So this point, -13/4. Now, how accurate do we have to be with -13/4? Well, that's a little bit past 3 in the negative direction. So 1, 2, 3, and 1/4. So I'm going to put it right here. Okay? Because remember, our graph will be this guy right here, this volcano, but upside down. So it might be a better way to describe that would be the abyss. I like it. Okay. All right. So we got the y-intercept down. So y-intercept, here we go to keep track of all our goodies. 0, comma, -13/4. If you don't know how I did -1/4 minus 3 and got -13/4, you can figure that out. That does not need to be an email to me. Figure it out. X-intercept still found the exact same way. We're going to set the y value equal to 0. And here we go. X-intercept should be something, comma 0. Well, what's something? It's the g of x function set equal to 0. So we're going to have to do some work on this bad boy. I might go a little different on this approach. I can always clear the denominator, but instead I might add 3 to both sides first and maybe cross multiply, which is the exact same thing as clearing the denominator, but that's okay. We're going to lie to you in earlier grades and tell you that it's a new fancy way to do things. It's really just clearing the denominator. So here's what I'm going to deal with. I'm going to move up here so we can follow along. I'm going to do 3 times that quantity. And that's going to equal -1. So let's see. I'm going to divide by 3. And I already know that I am done with this problem as of right here. Something squared is equal to a negative? What? That doesn't happen. You can't square something in the real number system and get a negative back. So that's not true. So that's not true. So that's not true. So that's not true. So I don't have any x-intercepts. So awesome. There are none. Let me erase that. X-intercepts? None. Which is phenomenal. So here we go. I got this y-intercept to hit, and then I got to do my best job of hugging these asymptotes. So here we go. Beautiful. Beautiful. Coming from the depths. Leveling off at -3. And there is a second graph. This is g of x in all its glory. It's the good stuff right there. All right. Do we have any more examples here? I don't know if I should do another one because I am boring myself. There's homework on here. All right. So you guys can try these homework problems 1, 2, and 3. It's really only two problems. The third one just says pick one of the graphs from the first slide. The very first slide was this one right here. So pick one of the graphs from the first slide and tell me why it lives in the quadrant that it lives. Signing off. Alexa, play Slayer. Oh, Alexa's broken. Is she making the ring?
No, it didn't even light up.
Alexa!
There you go.
Play Slayer!
Here's a station based on Slayer.